Good morning. Yeah, ladies and gentlemen, my name is Tsai from National Central University, Taiwan. And today's topic is about the development of the fast calculation stone surge system. And after we have a system, we have some case study about the 2013 Typhoon Haiyan or the local name Typhoon Yolanda case to see some stone surge propagation and inundation in the coastal regions. And especially in our team, we have Professor Choran Wu. He's my advisor, and I hope I can graduate maybe in 3 or 2 years, hopefully. Yeah. And from the computational resources team, we have a support team from the Sinica Greek Computing Center, and from Professor Simon Seeling and Dr. Eric Yang. And also, we have some support team from the atmospheric fields, the Professor Chan Yao Lin, and he's not here. Yeah. And we do the case study of 2013 Typhoon Yolanda case. Also, we get some data or support from the RCT in Philippines. Yeah. So thanks to your help. Okay, in the first, I would like to introduce some background of the stone surge. Maybe yesterday you have already heard about some phenomena about the stone surge. So maybe the stone surge is generated because of the tropical cyclones, storms, typhoons, or hurricanes, depending on where you are here. So in different countries, you have different names. And in Taiwan or in China, we will call the tropical cyclone about the typhoon. So in the sea level, you could see the sea level increasing because of the typhoon. So it's the typhoon ice. So in the sea level regions, you could see the water increasing because of a wind-driven surge and the pressure surge because of the typhoon is a vortex. So it will cause the abnormal water rising. And in here is the coastal regions. I borrowed some pictures from the wiki. It's the tidal effect with the stone surge. So imagine that if you buy a very expensive house living with your families, and suddenly the typhoon is coming. So when the stone surge aid some normal tides, it means that the total water elevation will higher than the normal tide. So the water will go very close to your house or your buildings. And in the same time, the waves under the stone surge will cause damage on your buildings or your house. So the stone surge also will have some interaction with the tide and with the wind wave. So the stone surge is very important with some physical interactions factors. In some cases, like the inundation induced by the stone surges, it's a very famous case happened in United States of America in 2005, Hurricane Katrina. In the left pictures, it shows that these are the buildings and these are the roads. The blue bodies are the waters. So it means that in these regions, the stone surge flooded these areas. And also in the right picture, you can see some bridges and the roads. So the community are flooded because of the stone surge. So also in the coastal regions, people living in these regions, we are under the threat of the stone surge inundation. So the stone surge inundation is directly relative to your life. And maybe I have no idea. We are fortunately or unfortunately, we Taiwan, Hong Kong, China, Philippines, Japan, and maybe Korea. We are located in very special regions. We are very close to the Pacific Ocean and South China Sea and the Japan Sea. Oh, cool. Okay, yeah. Okay, I solved this problem. So in these regions, we have enough energy and the water vapor or enough heat to make the tropical cyclone become a potential severe typhoon. So it means that we will have some problems generated because of a typhoon, like wind wave, stone surge, rainfall, or runoff. So in the right picture, it shows that the typhoon track accumulated from the 1951 to 2014. Taiwan and Philippines, yeah, we are under the threat of the typhoon's tracks. The red color means the typhoon's intensity is more than category 4. So in these regions, we sometimes we are faced with category 4 or category 5 typhoon intensity. And in Taiwan, maybe from the statistic results, we have 4 to 5 typhoons per year. But I believe that in Philippines, you should have more, right? More than 20. Oh, okay, 20. Yeah. So also, I think the Philippines will pay attention about the storm surge inundation issues. Okay, so in Taiwan now, I introduced some historical case about the typhoon inundation case. Is the Typhoon Dujen. The Typhoon Dujen is in 2015 September. Is the typhoon's track making landfall on the Taiwan's north part and then make a turn and then leaving the Taiwan and then directly to the China Fujian. So from the two pictures, you can see the inundation is some flooded, but the water level, the water height is maybe just 20 centimeter. But in some harbors, it's in Kinmen. Kinmen is located in these regions. In the Kinmen, the water level abnormal rising is higher than the seawall, so you can see water is flooded in the local harbor. And from the Central Weather Bureau's barometers, you could see the lowest pressure of the Typhoon Dujen is about 925 millibar, and the highest 1 meter wind is 200 kilometer per hour. So the typhoon is about the category 4 hurricane intensity. And how about in Hong Kong? We know that Hong Kong is not a big city, but actually in the past, Hong Kong was under the threat of the storm surge. It's the category 4 Typhoon Hagby. It happened in 2008. Also September is the typhoon track. The typhoon track is passed to. It's not directly passing to the Hong Kong, but just go to the China. But also it caused some damages. From some Hong Kong's local newspapers, you could see it described this storm surge about that it's like a small tsunami. Also, you could see the water, saltwater intrusion. This is the people, I think, is the buildings or hotels. So these roads are flooded because of the storm surge. And from the records of the storm surge at Victoria Harbours, Victoria Harbours is a very beautiful viewpoint. Yeah. So it's from the observation, we could see that it's the storm surge. The storm surge could be more than 1 meter. And the blue line is observation water elevation. The observation water elevation, if we move to the sea level, to the sea level 0, vertical, so it will be more higher than 2 meters. So it means that in the normal time, the storm surge makes the abnormal water elevation rising about 1 meter. Yeah, and now we go back to today's topic, Typhoon Yolanda, a Typhoon Haiyan issue in the Philippines. The typhoon life cycle is in 2013, November. It's just, I think the typhoon life cycle is about 8 days if we consider the tropical situation. The tropical cyclone situation. On this picture, some local newspapers describe this typhoon that it was like the end of the world. So we could see that the typhoon structure is very stable from the satellite image. From some field surveys at the local villages, you could see in a bridge or some fish villages or some seawalls, the scientific after the Typhoon Yolanda went to do some field survey, they find that the inundation height was measured at the bridge is 5.9 meter, and the run-up height would be 6.9 meter. And in these regions, the storm surge inundation it was measured the 5.0, but the seawall is about the 3.0 meter. So it means that the storm surge is higher than the seawall 2 meter. So it's a very dangerous storm surge. So in order to study this part of the storm surge modeling, we have some goals of the storm surge operational system or the storm surge modeling, and hope our model can adopt large enough computational domain on spherical coordinate system to cover the complete typhoon life cycle and full stone surge propagation. Because of that, when the typhoon generated, the typhoon track, we cannot understand the typhoon track. So, for example, maybe the different countries will predict the typhoon track. Maybe USA, they say that the typhoon will make landfall on the Taiwan, but other countries, maybe the wolf or some weather prediction system, they say no, the typhoon will make a turn before it making land of the Taiwan and turn to maybe the Japan or Korea. So from the weather system's prediction, they say very high, maybe the highly nonlinear uncertainty. So if we can adopt large computational domain, we can solve this problem because of we can cover the full stone surge propagation and complete typhoon life cycle to consider this issue. And also in our model, we hope that the model can include the nonlinear calculation and bottom shear stress and show the effects in the nearshore regions. And also we hope we can consider multi-scale stone surge propagation in the both open ocean and coastal regions because we hope our model can cover large computational domain and also focus on the coast regions and the offshore regions. And the most important thing is that the stone surge inundation is directly relative to our life. So we want to calculate the high resolution stone surge inundation for risk assessment. Also combined with the wolf model and combined with the global Thai model. And the most important thing is that we want our model will have high speed efficiency for the early warning system. Yeah, so here comes our model. Our model is based on the Concave tsunami model. It's Cornell multi-grid coupled tsunami model. You can use the nested grid system to calculate multi-scale stone surge propagation or tsunami propagation. So we use it to develop the stone surge model. And also this model now is being adopted by our official weather organization, Central Weather Bureau in Taiwan. So it is from the 2016, our model has become the official stone surge propagation system. So if you could go to the Central Weather Bureau's website, you could see our prediction results. But from 2016. So the governing equation we solve is nonlinear shallow water equation, and we cover the wind shear stress and the pressure gradient terms to cover the stone surge propagation in the different scales. And also we consider the bottom shear stress, and you can consider about the interaction with the bottom. And also the moving boundary scheme can calculate the stone surge inundation in coastal regions. And after we have a model, we need to do some model validation. So we choose a case, a benchmark problem. We compare our results with the solitary wave run-up experiment. It's done by Sinonakis. So the results is good, because the black line is our numerical results, and the dot, the red dot and the blue dot are from the experiments. So our results in the stone surge in a run-up calculation is very accurate. And our stone surge model can finish 2 days forecast just only in 3 minutes. And this model can use in the PC level's computer resources. So our model is very powerful. So we can divide our computational domain to different threads. And this work has already done and published our results on the ocean engineering is because of the contribution of the Professor Simon Sealing and Dr. Eric Yang, because of their help. So we can have the most powerful concave surge model. And in order to consider the typhoon's fields, we combine with the wolf model or typhoon wolf model in this study. And in order to consider the stone surge interaction with the tide, we combine with the global tide model, the TPEXL. The TPEXL is from United States of America's Oregon State University. So you can free download from the website. So they will provide the user interface of this model. Yeah. So after we combine with the global time model, we need to do the time validation. So it's very high accuracy. The bias in the specified locations is smaller than 0.1 meter, and the rule mean square error is smaller than 0.4 meter. So you could see from this picture, our results are very accurate. Yeah. Okay, so we need to do some local validation. So I choose the Taiwan regions and I choose the Typhoon 2015, Typhoon Soudelor to do the model validation before we go into the Typhoon Haiyan. So in order to consider the sea and the wind's jet coefficient, so we use the parabolic jet coefficient. It's published by the Nature's paper. You could see the when you are in the different winds in a different interval of the wind speed, you will have the different jet coefficient. So we will have find a very perfect curve about the parabolic curve. Yeah. So we have results. We combine with the observation data. The results are good in some locations like Suao, Nanwan, and Donggang and Kaohsiung. The results are good with after we compare with the observation data. So also in the stone surge calculation in coastal regions, we can see in the Pingtung, we can see some stone surge flooded or inundation if we compare with the pure type. So it means that when we are facing a stone surge, we will be under the dangers. So now we go back to study the case study of 2013 Typhoon Yolanda. It's the Yolanda's track passing through the Guylian and Tacloban, and then to the China. So we can expect that we will have a highly stone surge in these regions, especially in Guylian. I remember that in the Guylian, the water recorded is about maybe more than 3 or 4 meters. Yeah. So in this case, we use the O-level netted computational domain. In the first layer, we want to cover the complete typhoon life cycle. So we use a very large domain on spherical coordinate system. The resolution is about 4 kilometers. And the second layer, we use the 1 kilometer resolution to cover the offshore hydrostatic stone surge propagation. And the near shore and coastal regions, we use the 500 meters domain and 100 meters domain in the Leyte Gulf to focus on its stone tide and stone surge phenomenon. So we combine with the Wolf model to give us the forcing. So it's about the pressure field and wind fields. Wolf results are done by Professor Rin Chuan Yao in Sinica. So you could see is the typhoon's central pressure and the wind field and passing through the Guylian and the central Philippines. So we use the Wolf results input to our concave stone surge model. You can see the water rising. In these regions, they are because of the pressure gradient, because the pressure gradient in the deep water is significant. But when the typhoon center is closer to the coast regions, the wind shear stress will become significant. So from some snapshot of the stone surge in the Philippines, you can see some details about the stone surge propagation when the typhoon is passing the Philippines. So before maybe when in the center, the water elevation is rising because of the pressure gradient directly, and then when in some coastlines, they are generated because of the wind shear stress. So the maxima stimulated stone tide and Leyte Gulf, in the right side and the left side, we could see the maxima value is more than 1.3 or 1.3 meter. In the Tagunian, the stone surge is more than 1 meter, 1.2 meter. And from our results can also combine with the Google Earth and the Google Map software, so we could see some local names of places. And later, so I have few minutes, so I will introduce some stone surge operation system about in Taiwan how we can do the stone surge prediction. So when we know that we will have a typhoon, we will start our prediction model and get some input. The input will from maybe the parametric typhoon model and the WRF or TWRF model. If we use the parametric model, we will run a cycle for 3 hours. So it means that the 3 hours we predict, and after the next 3 hours, we predict again and do again and again and again until the typhoon is leaving. And also the TWRF is doing. So the input is about the meteorological forcing and the tidal boundary condition. And the tidal boundary condition are from the Oregon State University's T-Pexel 7.1 module. In our results and our products, it's about the 2 days predicted storm tide and the pure tide at 34 specified locations and 2-dimensional pictures and animations to help the forecasters to see the results. So examples about how do you run the storm tide and the pure tide. So is the tide point when the forecaster will start the system. So we will do the 2 days forecast and we need to do the 2 days warm up. And the pure tide do not worry about the warm up issue. So we just do. Yeah. So it's just some picture to make you understand the prediction. So our model can compare with other countries' operational storm surge model. Maybe in the USA, they use the slush. In the USA or China, they also use the circ. In Japan, they use the JNA model. In Korea, I have no idea. Maybe they use the pump, but you have a different name about the storm. Yeah, but also the storm is based on the pump model. In Taiwan, now we are using the Comcast storm surge model. So the resolution in the Taiwan, because our Taiwan is not so big. So the resolution in our Taiwan could be 1 kilometer. And our coordinate system is under the spherical coordinate system. If you have some interest about the inundation, so also we can use the Cartesian coordinate system. But maybe in the USA, they can use the polar coordinate system. Yeah, so it's the difference from our model. And the grid system, maybe we can use the nested grid system. But in the Earth circle, they use unstructured grid. Unstructured grid is very time-consuming. So you need to use very expensive computational resources to solve this problem. And also we can calculate the inundation. But maybe in Japan or Korea, they cannot calculate the inundation. And also in our model, we can cover the nonlinear tidal effects. But the USA or Japan, they cannot because they just calculate the storm surge and plus the tide results directly. So it's the tide validation. In this location, it shows that the results are very accurate. And here is some a practical case study. It's the 2016 Category 5 Typhoon report in Taiwan. Is the typhoon's tracks, and also the wind structure are very stable. So in some operational case, you could show that in the 2 days forecast, how typhoons the storm surge, a maximum storm surge in the deep water. So the storm surge is more than 1 meter. So it means that the storm surge is very dangerous in the spatial regions. Yeah. So if we compare with some local news, it says that we will have a surge and wave in the east part of the Taiwan. So it compare well with our results in these regions, because in these regions we can see the storm surge, maybe not a storm surge, the highest storm tide minus the highest tide is more than 1 meter. So in this day, we will have 1 meter abnormal water rising in East Taiwan. So if we compare with the local newspaper, the results is not bad. Yeah, so it's the severe typhoon Meranti last year. The typhoon Meranti, the intensity is very strong. The central pressure, it will reach the 900 millibar. So 900 millibar is more, it can reach to the Category 5 typhoon. So in the typhoon Meranti, we could also see the maximum storm surge in the duration of the different time. It's about during the 12 hours, the 12 hour to 24 hours is about half day, and half day. It means that the typhoon is leaving Taiwan. And also, we want to study the contribution of the wind shear stress and pressure gradient. So in the Taixi location and the Nanwan location, the contribution of the wind shear stress maybe in these regions is the maximum wind surge is about 0.4, but the pressure surge is 0.5. So when you plus, we can maybe get the stone surge is about close to the 1 meter. But the maximum wind surge and the maximum pressure surge, the time point is not the same. So you cannot just plus these results directly. But in Taiwan, we can see a very spatial issue. The wind surge is not so high. It's just 0.1 meter. But the maximum surge generated because of the pressure gradient, it can reach to 1.2 meter because of the typhoon center is passing through this location directly. So the water rising is significant because of the pressure. Yeah, so also is the contribution in the other locations. Okay, so in here we show some three-dimensional demonstration about these results. We could see this stone surge generated because of meteorological fields and then passing to Taiwan. So in these regions, Taiwan and China, we have abnormal water rising focused on these regions. Okay, so here I have concluded our modules. Our stone surge model can provide some product about a high resolution potential inundation areas and predict the water elevation at specified tidal stations, and give everyone and give users about the maximum water elevation in coastal regions. So our model can adopt large computational domain to cover the complete typhoon life cycle and full stone surge propagation. And resolution in coastal regions, can be very easily promoted and be separated, calculated in negative grid scheme, and combined with a WOLF or T-WOLF model, and combined with global tide model. Yes, and the speed is very high, so we can do the operational system and early warning system. And now our model has been the official operation system at Central Weather Bureau from 2016. Yes. Okay. Yeah. Thanks for.